Thank you for the introduction. Yeah, thank you. Thank you for the introduction. My co-authors are Tim Dinte, Stefan Schneegass, Florian and Rohs. And I will talk about cruise control for pedestrian. Our approach for controlling walking direction while using electrical muscle stimulation. I guess you all know these scenarios while user walking through in the everyday life while interacting with their mobiles. Of course, such things could happen if you do so. So I guess you perhaps expect that the person will run into this lamppost. But we envision that the user could be steered successfully around this lamppost while reading this book and getting back to this path afterwards. We're doing this, or we try to achieve this, by using electric muscle stimulation to actuate one muscle of the upper leg. We call this approach Actuated Navigation. In the following, I will classify different navigation scenarios which are actually working at the moment. Current navigation works like this. A user has a mobile and a navigation system to get to a certain point. The navigation information or navigation cues are transmitted to the user using the auditory or visual channels. The user perceives these cues and is visual connected to the, or is looked at the mobile during the navigation. Then he needs to interpret these navigation cues and translate it into a movement to actuate the legs to changing the walking direction. Finally, the position is be updated by the navigation system to the navigation model. These approaches have several drawbacks. For example, the visual attention, as you saw in the video, is on a mobile device. And if you pay attention to your surrounding, then it could be happen that you're overlooking one of these information that we got in one direction. Finally, it's difficult to align the virtual map to the real world, what always happened to me. To overcome these problems, several projects uses Vibro-Tactile feedback. This applies to the user's body and transmit the navigation cues. The active belt uses 7 different vibration motors to indicate different changes of the walking direction. So in this case, the vibration feedback or the Vibro-Tactile feedback is applied to the user body. The user perceives this information and interpret these information and map them, or these navigation cues, and maps them to the real world. Afterwards, he actuates his legs to change the working direction. And then, of course, the map is updated. These tactile feedback frees the auditory and visual senses of the user. The user can focus again on the environment. The cues still need to be interpreted by the user. The interpretation process a mental load, and the user can't miss one of these cues. Others have tried to actuate the body as an indicator to simplify these. Possessed hand use electrical muscle stimulation to actuate the user's hand. The hand indicates the direction in which the user is supposed to walk. the user becomes the output device in this case. In this example, the actuation signal is directly applied to the user's body, and the and this lets the user become to the indicator device. Then the user perceives this indicated direction, and he needs to interpret these cues and map them to the real world. The direct mapping is easier to understand. If you know one direction, then you just can follow it. But still, you can overlook and or misinterpret these cues. The interpretation still needs cognitive loads, so you need to think about it. The galvanic vestibular stimulation manipulates the sense of balance. The electrodes applied a constant current behind the ears. The GVS brings the user shortly out of balance, and this results the user slightly goes sideways to one direction. In this case, the navigation system directly manipulates the walking direction. The user does not need anymore to interpret the navigation cues. She just tilts, as you see in the video, to the direction where she is supposed to go. One drawback of this solution is that it's applied to the upper body, and the walking direction, the walking pattern becomes unstable. In our approach, we directly manipulate the locomotor system of the user. To do so, we are using electrical muscle stimulation. We actuate the sartorius muscle. The sartorius muscle connects the hip to the knee, as you see on the video. To actuate this muscle, we place self-sticking electrodes on the skin over the muscle, and an exact placement is very important to get an actuation effect. When actuating this muscle, the leg rotates outwards, as you see on the video. If you do this while walking, you're making a right turn. To explore this effect, to explore this effect in a user study, we developed a wearable prototype. We used a mobile to calibrate the strength for each user and to apply the EMS signal to the lower leg. We control the EMS signal with a mobile via Bluetooth with these control boards. To generate the EMS signal, we use an off-the-shelf massage device on the top and self-sticking electrodes. To investigate the actuation effects on walking, we conducted two studies. The first is about the first was in our lab, and the second was in our outdoor scenario. First, we investigated different stimulation strengths and how they influence the walking. The goal was to quantify the amount of deviation while walking. We invited 18 participants with an average age of 22 years. We used a within-subject study design. Each user had to work with a strong, medium, and weak EMS signal on each leg. We repeated this condition 5 times, and as baseline, we let the users walk without EMS. In the beginning of the study, we calibrate the strengths for each user individually. We placed the electrodes over the sartorius to see if there is an effect of the construction. This after the calibration identifies the maximum level which is still comfortable for the users. We use this. We divide this level or this angle of this level into 2/3 and 1/3 of the maximum level. These are the strong, medium, and weak levels what we are using in the study. At this point, we had to execute 3 users because the actuation didn't show any response. Not shown. After the calibration, we blindfolded the participants and placed them in our tracking area. We had to execute another participant for technical reasons. The first trial was without signal. This trial is with a signal. The experimenter always apply the signal during the stringing phase of the lake. Each user had to perform 40 trials. In a total, we recorded 700 trajectories. These are the trajectories of all users. As you see, there's a quite large variability between the users. If you have a look at user 3 and user 7, you see there's only a small effect. In contrast, for user 14 and user 18, there's a large effect. Overall, we observed a direction change about 16 degrees per meters. When we split the data, then we see this figure. As you see, a stronger signal results a larger deviation. However, because of the large variability, the differences are not significant. To investigate or to evaluate these results, what we found in the lab study, we conducted an outdoor study. For that outdoor study, we choose 2 routes, one on existing trails, left, and one on lawn without a visible path. This study was conducted as Wizard of Oz study. The experimenters followed the participant to control them remotely. We invited 4 participants and calibrated them in the lab and brought them to the park. The participants neither knew the route nor the endpoint. They got the instruction to walk, relax, and let the system steer them. We also introduced them to pay attention on the surrounding. After the study, we interviewed them, and the feedback was quite well. The user was surprised how well the system works. The participant felt really like guided by the system. One participant remarked, "I was turned around the corner." We think that there are a lot of different possible application scenarios. Actually, one is a mobile tourist guide which guided the users through a city while looking at the environment without focusing on the navigation task. The second, the system could choose different jogging routes or jogging trails depending on the daily performance or daily training plan. Also, we envision that this kind of technology could allow a variety of new team sports. For example, the coach may influence the player movements from the outside of the field. Maybe Bayern Munich already has one of these systems because they played so well last night. However, there are a number of challenges. The first is that the user needs to be willing to wear such electrodes. The second is that the electrode placement needs to be quite accurate. The third is, as you saw in the slides, there's a large variability between the actuation of the users. We think that these challenges can be solved in the long term. For example, we are using really simple electrodes, but there are already advantage grids of electrodes outside. To conclude my work, we have shown a concept to manipulate the walking direction for pedestrian. We investigate the concept in a lab and in an outdoor study. Thank you for your attention. I'm happy to answer your questions.
All right, Patrick Baudisch, Hasselplatten Institute. Awesome work. I really, really like this. I also have no issues wearing electrodes, so I really don't. So I hate doing this. I hate asking the hard question, but because I really like this work. But there's one thing that I'm just wondering about, which is the potential confound in the study. Right? We work with electrical muscle stimulation. We're quite familiar with this. So how do you really know that you? And then how would you find out that you actually made these people turn compared to instructing them and they actually cognitively did the thing, right?
Yeah.
How would you do study design? Because it's possible, it's just very, very hard to do. So what's your take on that?
Yeah, I think actually you thought already about these problems because we can't really say 100% if it's like guidance or if they really make the turn by the rotations, because you always feel the electrical stimulus on your leg, so
yes.
You can't say if it's like walking to one direction. We actually asked the users, and the user said that's like around 10% is by guidance and 90% by the actuation. But you can
don't change that.
Yeah, but you can like do different given a different task, a mental load task, and doing while walking, and
it is
that they can't really like concentrate on the movement, but still you need to get rid of this feeling to get sure that they really they make this movement.
I think, because from an engineering perspective, this is great and this works. So from an engineering, if I wear my engineering hat, either are fine. That's all good, right? Because Pedro and I've been working on this, and the whole time we debated do we have to paralyze muscles and so on. Do we need to, what part of the cognitive system we need to turn out to kind of get these information.
Actually,
this could be a super cool follow-up paper for you guys for next year to find out which one you have.
Yeah, we definitely have to concentrate on this, but we maybe later talk about this, or I talk to Pedro how you solve this. Yeah. Thank you. Yeah, actually, in the interview we had a question about this as well, because the actuation of this muscle only rotate your leg to the outside, and you easily can override the signal. So if you don't want to go to one direction, you just can move to the other direction, or if you stand still, nothing happens. So the participant mentioned that if they always stay into control to change the direction on their own, then it's no problem. They don't have any doubts about this.